Hi everyone, welcome to my video explaining the solutions for the data synthesis ML task second round set A. Today I will walk you through four challenging algorithm questions that combine data structure, algorithm, and machine learning applications. Let's start with question 1. Design given an aerial tree storing numeric values, design an algorithm to efficiently return the sum of all values within a given range L to R. The follow-up asks how this approach scales if each tree update must propagate features for downstream ML models. An ABL tree is a self-balancing binary search tree where the height difference between left and right subtrees is at most. This ensures overflogging operations for search, insert, and delete. The key insight for range sum queries is to maintain subtree sums at each node. When we insert a value, we update the subtree sum by adding the value to the current node sum. During rotations, we recalculate subtree sums for affected nodes. For a range query L to R, we traverse the tree intelligently. If current node value less than L, we only search the right subtree. If current node value greater than R, we only search the right subtree. If the value is in range, we include it and search both subtrees. This gives us O of log n plus k time complexity, where k is the number of elements in the range. Now for the ML follow-up, when each update must propagate features for downstream models, we extend the AVL tree with a feature cache. Each node stores computed features like subtree, mean, balance factor, and height. During insertions and rotations, we propagate these features up the tree. The trade-off is additional memory for the cache and computation during updates, but this ensures downstream ML models always have fresh, consistent features with recomputation. So moving to question number 2. Suppose you must store and retrieve large model weight files distributed across a database. Explain how a B-tree supports first search and insert operations at scale. The follow-up asks how this applies to feature vector lookups in recommender systems. B-trees are multi-way search trees designed for disk-based storage. Unlike binary trees, each node can have many children up to where D is the degree. This creates a very bushy tree with minimal height. For model weight storage, we will use the B tree as an index mapping model IDs to file metadata. The actual weight files are stored on disk and serialized with Pickle. Search operations take O of log D n time, and insertions maintain balance through node splitting. The beauty of B-trees is their disk friendliness. Nodes aligned with these block sizes and the high branching factor means fewer disks. For large model files, this is crucial because each level access might require a disk read. For the recommender system follow-up, we create a feature vector index using B-trees. User IDs serve as keys, storing feature vectors and pre-computed norms. The range search capability allows batch retrieval of vectors for similar user IDs, which is common in collaborative filtering. Cosine similarity calculations happen on retrieved vectors, and we can find their most similar users efficiently. This scales beautifully because we handle millions of users while maintaining logarithmic search times. Now moving on to question number 3. A minimum spanning tree connects all nodes with minimum total edge weight and no cycles. In distributed systems, we need algorithms that minimize communication. Borovka's algorithm is naturally distributed. Each component finds its minimum weight outgoing edge, then components merge. This runs in O of log n rounds, with each round potentially having components. The implementation shows two approaches: Borovka's simpler method and the more sophisticated GHS algorithm with better message complexity. For the ML application in sensor networks, each sensor represents a feature and edge weights are computed as one-minus correlation between sensor readings, and the MST connects all sensors while minimizing redundant information. Highly correlated sensors appear in the same branches, so we can select representative features by choosing one sensor per branch. This reduces the feature space while maintaining diversity. The optimized sensor placement method extends by the k-1 heaviest edges to create k clusters. Each cluster contains highly correlated sensors, so we only need one sensor per cluster. Real-world applications include IoT networks where communication costs require minimizing active sensors and feature engineering where removing correlated features improves model generalization. Finally, question 4. For a tree or graph-based feature index in a memory constrained environment, compare slab allocation versus garbage allocation as memory management strategies. The follow-up asks which option better supports predictable latency for online serving in ML system. This question compares two fundamental memory management approaches for real-time ML systems. Slab allocation pre-allocates fixed size memory blocks organized into slab. Each object each object type gets its own slab rule, providing O of one allocation and deallocation with predictable latency. No fragmentation for uniform sized objects, but memory can be shared across types. Garbage collection offers automatic memory management with flexible object sizes, but introduces unpredictable cost times during collection cycles. Mark and sweep traces reachable objects, then reclaims unreachable memory. Compaction reduces fragmentation but adds cost time. For online ML serving with strict SRS, slab allocation is strongly preferred. The benchmark shows slab allocation has consistent latency across operations, while GC exhibits occasional spikes. P99 latency ratios quantify this slab typically maintains 1.5 to 2x ratios, while GC can see 5 to 10x during collection. In production ML systems, feature indexes must serve predictions with bounded latency. A recommendation system can tolerate 100 ms GC pauses when serving with 50 ms SLS. The slab-based feature index uses thread safe slab allocation for feature vectors, providing deterministic memory operations. This approach is used in high-performance systems like engines, Redis, and trading platforms. The trade-off is manual memory management complexity, but for latency-critical ML serving, this complexity ensures strict performance guarantees. The, that's all for questions we have covered. The key themes are how fundamental data structures and algorithms enable a scalable ML systems. Each solution balances performance, scalability, and real-world constraints. Thanks for watching. If you found this helpful, please uh, feel free to ask questions in the comments about any of this implementation on their ML applications. Thank you.